Hello, we are going to continue our exploration of segment trees. And where we left off last time is we understood how a segment tree worked, and I was getting a bit tired. Actually, we're six. I only have 30 minutes right now because someone's going to come and visit the house in 30 minutes, but then I hopefully will resume a bit after this. Um, Anyways, segment trees allow us to do queries and updates in all of login time. And the way we build it is by updating these intervals. And so we're going to try our shot at implementing a segment tree. And I think what we can do is they have the, is this CSU? No, that's not Yusuko, right? And then segment tree, is that in gold or segment tree? Auditor grabs trees. So I think maybe silver has segment trees, or is it platinum that has gold tree auditor? Problems? What's the rating of this? Like, I think segment trees are like 1600 rated problems. Generally. Or more. Don't know why it's taking so long. Okay. So let's look at this problem. The king is making a knight tournament. The king has raised messages to all knights. I'm a peasant, yes. This applies in real life. There's no surprise that you slept in this morning and were late for the tournament. It was a weekend after all. Now you're really curious about the result of the tournament. This time the tournament, there are n knights. Each knight is assigned a unique number. Huh. Let me see. So xi, so 1 1, 1 to 3, and then 3 1. 2 is already out. And then 1 to 4 is guaranteed. So the easiest way is to brute force. You want to know for knight number 1, right? He stayed here. So if it's in this range and then he disappeared, then it's the winner. Else, like you could just binary search this, or like at some point they exist and at some point they don't. Like at some point they're in and at some point they're not. So that would run of an m, which is too slow. Right? Like the idea is you go through all the fights and then you keep track of like for each of these. At some point they get eliminated, or if they're the winner, then it's going to be 0. So from the first query, we know that any number except this one, they will have been defeated. And then similarly, when we have 3, any number that's not in this interval, so 1 and 2, will have 3 as the answer unless they've already been eliminated. So how do we do this? It's like a range query. Like if we do union find, that could work, where you start with n nodes, which are each its own set, and then 1, 2, you're going to go from 1 I to 2, and then all of them are going to be together, and then the leader is just 1. Alright, so 1 to 2 is 1. And then all of these will point to 1. Right? Yeah, there's like pointers, and then when you do 1 to 3, 1 is the head. So 1, all the numbers that are not 1, but you still have to iterate through all of these numbers, right? Like how do you know? It's contiguous. So how can this be segment tree? Guarantee at least 2 knights took part in each battle. So we have the guarantee here. Yeah, it's all about like being able to visualize it in some way. So I'm struggling to come up with the idea fast. But to come up with the idea fast, you need to have seen, certain amount of problems, or you just need to be smart. So I haven't seen as many problems, but I can be smart. Or I think I'm smart, but I don't think I'm smart. Actually, you are what you believe, so I believe I'm smart, so I can believe, so then I'll be smart. What? Mm. Mm. Yeah, I don't know how to do this. Right, but there are many fights. If it's m How is this? Okay, and how can you solve this with a segment tree? Use a set, but it's actually really simple. So basically, you maintain a set of all this knights. You start from all the knights, and then when you have an interval, you iterate through the set until you empty it, and then you select empty everyone. And then in the next interval, you will search, because the set under the hood is just a binary tree, a self-balancing binary tree, I assume, right? Binary search tree. And so you can always find it in log n. And so you have k log n. But I guess the upper bound is fine because it's not O of nk, because O of nk means for each of them it would be k, but it's actually amortized to k total. N times n plus k log n. Which is fine. Where k is equal to n, so it's O n log n. Oh. Okay, so I wanted to do segment trees, but I guess we can do this problem. I guess I was not convinced that, yeah, I saw it was being O of nm, but if I saw that I could make it O of m plus n log n, then it would be fine because each of them is n log n. And so you see this interval, and then instead of going through the interval, you sort of search through that interval by calling log, and so it's log of n for each query, and then so that's n log n, and as the number of alive nights decrease, then your queries will be fewer and fewer. So this is an older one, so they'll just take nm, and then for I equals 0, I less than n, or I plus plus, alive, so lower bound returns, okay, well, cur and cur is less or equal r, erase, right? And then you need to figure out ends at and then 314. And if our analysis is correct, this should be, we should be able to run it in of n plus k log n. Dude, this color is so ugly. Yeah, guys, I did pretty bad on a contest. I did really bad because I could not think of like how to do B, or I think I just like fumbled. But it happens, you know. Trust the process. Okay, accepted. All right, cool. Yeah, but that wasn't really a segment tree problem. And colony. What the hell? How hard is this problem? Why is it F? Okay, we need more segment trees. Two to the n. So I see you do pairwise, you do OR, and then you do XOR. And so okay. So, I mean, if you just brute forced it, you would, there are 2n nodes, so for each node, you would just compute it. I see. Okay, so if you update it, the ORs are going to change for... Oh. Yeah, OR is an update. Okay, so this is a classic segment tree problem, right? We're going to, and it makes our life pretty easy because it's to the power of n, and then we're going to attempt to do some updates, or okay, this is not too bad. Did I just change B by accident? Oh no, 197. We need D. So we have int nm and m, and then ints to seg tree, and then we're gonna just use 2 times n because it's a power of 2, which means that there are exactly 2n minus 1 different nodes, right? So if you have 2 nodes as the children, you have 2n minus 1, which is 3, right? If you have 4, then you have 7, which is 2 times 4. Okay, perfect. And then what we're going to do is build the initial segment tree. So for int I equals 0, I less than n I plus plus, and so it starts from index n. So we're gonna build the root nodes, or the leaf nodes. So 0 is gonna represent the range across the entire tree. So sin seg tree at I plus n. That's how we want to do it. And then we're gonna build. And then build, which is going to be recursive, and then it's going to take and then like we'll recursively call it, and then like build left. If depth modulo 2 equals zero, else if I greater than 2 times return. We're gonna just, I think it's easier to just pass the seg tree by reference. And then it's like seg tree 2 times I. Oh, but we need it 1 indexed. We're gonna build it like this. We're gonna do it in post order traversal. So 2 times I plus 1, def plus 1, and then if and then what's gonna happen is we're gonna do, what is it? You do so it's OR and an XOR and an OR and an XOR. So, and then what we're gonna do is like, we'll call build seg tree 1, 0, and then what's the depth? This should be 1. So if our total depth minus the depth is equal to 0. All right, so let's start with the simplest example 1, and you're at depth 1. You're gonna do XOR. Also, you do an OR, right? So if we're at 0 and then the depth is 1, then that means that we're taking an OR. Seg tree at I equals seg tree at 2 times I, or seg tree 2 times I plus 1. So that's how we build a segment tree. And then when we query, we want to take again the segment tree. And then we want, so there's query and then there's update. Let's do query first. So if left query equals our query, return and then we're gonna is one indexed. So 0 index is not used. Index 1, index n plus 1 is going to be used for that last row. I think this is right. And mquery. So our query is actually really simple. Our seg tree at index 1. So the update is what we need to do here. Void update. So yeah, I visualized it as top down. I guess is the update also post order? How is the update? I believe it is post order. Get max update. Yeah, so you call it, it's post order. All right, got it. Oh. Someone's supposed to knock on our door. Okay, I will end it here right now. And I'll finish it, but someone's supposed to knock on our door.